Welcome to the Explainer. Today, we're going to dig into something truly fascinating, one of the biggest leaps in artificial intelligence, really. We're talking about how machines went from just seeing text as, a jumble of letters to actually understanding what words mean.
Okay, so let's just start with a really simple question that, believe it or not, completely stumped early AI. You and I, we know cat and kitten are super related, right? They're basically the same idea. But how on earth does a computer, which just sees a bunch of ones and zeros, figure that out? It's a surprisingly tricky problem.
All right, so to solve this, the very first step was trying to translate our language into their language. And their language is numbers. But as we're about to see, this first attempt had a massive, massive blind spot.
So the first crack at this was an idea called one-hot encoding, and it was pretty straightforward. Imagine you have this gigantic light switch panel, okay? With one switch for every single word in the English language. To represent the word hotel, you just find that switch, you flip it to on, and you leave all the millions of other switches off. Simple, right? Well, there's a huge flaw.
And here is the problem in a nutshell. To the computer, the vector for hotel and the vector for motel are just two totally different light switches that happen to be on. There's zero connection between them. The computer sees them as being just as different as hotel and, aardvark. It's a complete dead end if you want to actually understand meaning.
So, yeah, that whole one-hot encoding thing, it was a bust. So, researchers went back to the drawing board and they tried a totally new tactic. Instead of just giving each word its own unique ID, they thought, hey, what if we just start counting them? Now, this got us a little bit closer, but it was still missing the real point.
The next idea was literally to just count words. A technique called bag of words did exactly what it sounds like. It's like you dump all the words from a document into a bag, shake it up, and just count how many of each you have. And look, it was a step up for some things, like sorting news articles by topic, but at the end of the day, it was still just counting. The words themselves had no meaning.
So here's the bottom line. These counting methods were completely blind to what words actually mean. They had no idea about context or semantics. In this world, the word cat and kitten are just as different from each other as cat and car. We were still fundamentally missing that key ingredient.
And that brings us to the conceptual breakthrough. This is the idea that completely changed the game for language AI. Seriously, this was the big aha moment where everything clicked. And what's wild is that the breakthrough came from an idea that's way older than you might think. We're talking 1957, from a linguist named J.R. Firth. And he said this one thing: you shall know a word by the company it keeps. That single sentence, it unlocked everything. The idea itself is just brilliantly simple. Think about it. A word's meaning isn't just some dusty dictionary definition. No, it's defined by the other words it hangs out with, its context. The words that always show up around kitten, words like cute, fluffy, playful, meow, that's what gives it its meaning.
So this incredible idea led directly to a powerful new technique called word-to-vec. And this is what finally took that elegant theory and turned it into a mathematical reality that a computer could actually use.
So how does this whole thing work? Well, basically, word2vec learns by playing a giant game of fill-in-the-blank on billions of sentences. One version, called SIBO, looks at the words around a blank and tries to guess the missing word. The other, called skipgram, does the opposite. It takes one word and tries to predict its neighbors. Through this process of just constant prediction and self-correction, over and over, the AI starts to learn the relationships between words. And the result of all of this training, well, it's something pretty remarkable. We're not dealing with a simple list of numbers anymore. What we get is a map of meaning.
Okay, this is where the magic really happens. After all that training, every single word gets a set of coordinates, what we call a vector, that places it on this amazing multi-dimensional map. And words with similar meanings, they end up as neighbors on the map. So suddenly, king and prince are clustered together, so are woman and girl. For the very first time, the computer has a way to understand similarity. And because these coordinates are actual mathematical vectors, we can now do something that honestly just feels like magic. We can do math with words. We can actually perform arithmetic on them to uncover these hidden relationships in our own language.
So check this out. This is the classic example, and it will absolutely blow your mind. If you take the vector that represents the word king, and then you subtract the vector for man, and then you add the vector for woman,
the answer you get is a vector that is incredibly close to the vector for queen. Now stop and think about that for a second. Nobody taught the model about royalty. Nobody taught it about gender. It learned these abstract concepts of power and gender entirely on its own, just by looking at the company words keep.
And this is not just some cool party trick, okay? This is the engine behind so much of the AI we use every single day. You know when your music app recommends a new song because it's similar to one you like? That's word embeddings at work. When Google Translate actually captures the nuance of a sentence, that's this deep understanding of meaning.
So this is all incredible, right? I mean, it's a huge breakthrough. But this technique, which created what we call static embeddings, has one pretty significant limitation. Every word gets one and only one fixed meaning, one fixed vector representation.
And that leaves us with a brand new puzzle. Think about a word like bank. How can a single static set of coordinates possibly represent both a riverbank and a financial bank? The meaning depends entirely on the context. And solving that problem, well, that's the next great challenge that AI had to tackle.